Okay, I'm back, and now let's talk about the birth of the universe. So you got to know how old the universe is. So we think that the universe is about 14 billion years old. And you also need to know what is the Big Bang theory. So the Big Bang theory says that the universe begins as a small, concentrated, highly high temperature, high energy, and fundamental particles and fundamental forces initially. And then after the Big Bang, the universe begins to expand and it begins to cool off, and you start to build up more and more complicated structures. Okay, so what should you know about the Big Bang theory? Okay, so you should know the evidence for the Big Bang theory, so that galaxies are moving away from the Earth today. And so that means if you go backwards, the galaxies in the universe will come together. Okay, another thing that you need to know is that the more concentrated something becomes, the higher its temperature is going to be. And so eventually the temperature is going to be so high that matter as we know it today will begin to break down into more simple particles. And those simplest particles that we know of are going to be called quarks. So that after the Big Bang occurs, the universe is going to consist of quarks, and then those particles are going to become more and more concentrated and complicated. Okay, so you should know that quarks are inside of protons and neutrons. And then protons and neutrons are inside the nucleus of an atom. And then the nucleus is inside of an atom so that the electrons are in orbit around it. So this is the order that materials developed after the Big Bang. So initially, you had the universe was composed of matter quarks and antimatter quarks, and they would go together and annihilate each other and turn into pure energy. But that energy could turn back into matter because E equals mc squared. So that's Einstein's famous equation that relates energy to mass. Okay, so that these quarks and antiquarks would combine, turn into energy, but then the energy released was capable of creating quarks and antiquarks. But this did not last for very long. So as the universe continued to expand, it's beginning to cool off. And eventually it got so cool that the matter and antimatter were able to go together again and turn into energy, but there wasn't enough energy to be able to make matter and antimatter. So eventually the universe consisted only of quarks. Okay, then the next thing that's going to happen is those quarks are going to combine and turn into protons and neutrons. Okay, then the next thing that's going to happen is that those protons and neutrons are going to start to slam together to make the first nucleuses. And this is going to make primarily helium. And it didn't make any more elements in the periodic table because the temperature is continuing to cool off. And so it takes a lot more temperature in order to make those heavier elements. And so it was only able to make helium and just a little bit of lithium. So that's the reason why in outer space, the universe consists of about 75% hydrogen and about 25% helium. So that 25% helium is a result of the Big Bang. Okay, then it starts to cool off further, and eventually electrons are going to attach themselves to those nucleuses to make the first atoms. Okay, then those atoms are going to get into big clouds, which we're going to call nebulas, and then gravity is going to cause those nebulas to collapse and turn into the first stars. And then we call these first clusters of stars globular clusters, and then as they began to collide with each other, that's what made the first galaxies. So that's kind of a summary of the Big Bang and what happened during the Big Bang. And so I encourage you to read through this chart, which is again a summary of everything that happened after the Big Bang. Okay, so if the Big Bang created hydrogen and it created about 25% helium, where then did all the other elements in the periodic table come from? So they are manufactured in stars. So as a star is living, it takes hydrogen and smashes it together to make helium. So all stars do this. They convert hydrogen into helium. But when they begin to run out of hydrogen, they begin to die. And so the cores of these stars begin to collapse because the only thing that was keeping the core from collapsing was the nuclear explosions. So as soon as it starts to run out of hydrogen, the nuclear explosions begin to die down, and so gravity's taking over, and gravity's causing the cores of these stars to collapse. So as they're collapsing, they're heating up. And if the temperature can get high enough, then helium can be fused into the next element the next main element in the periodic table, which is going to be carbon. And our sun will be able to do this. Now the outer layers of the star, which is mostly hydrogen, but it also could have some other elements, is going to expand to become a red giant. And then as the star completely dies, that is jettisoned into outer space as a planetary nebula. So that means the universe is enriched in the hydrogen and those other elements that were in the outer part of the star. Okay, now the core of the star is eventually just going to cool off and turns into a black dwarf. Okay, if it's a bigger star, then as it dies, it can make heavier elements than carbon. And so we build up the elements in the periodic table up to iron as a star is dying. Okay, then if it manufactures iron, that's really, really bad for the star. Because if you slam iron together, nothing happens. It doesn't give off any energy. So that means the core is really going to collapse because now there's no more nuclear explosions pushing outwards. And so then the star is going to detonate in a supernova, and that's going to release so much energy it can manufacture all the other heavier elements in the periodic table. So to summarize, hydrogen and helium are born in the Big Bang. Okay, more helium and the other elements up to iron are manufactured as a star is dying, and then when a star explodes, it can manufacture the elements heavier than iron in the periodic table. All right, let's take a break, and when we come back, we're going to go through the formation of our solar system.